Welcome everyone to part two of this video series on material selection and the specific case study that we are doing for material selection for towing cables used in automobiles. Now, this is scenario two in this part two of the video, where we are going to treat area as the free variable. And if you want to see the details of the part one, you can go back and watch that video, but I'll give you a very quick recap of what happened in the part one. So in the part one, we started by considering the problem in the scenario one with a lot of fixed constraints, and we had the length, the force, the maximum deflection, the maximum possible weight, and the factor of safety, all of them prescribed, and even the diameter was prescribed. And then we went forward and we tried to select the best material and minimize the cost and have the cost as one of the objectives to reduce. And based on our constraints, we were able to then find a particular material that we selected in this case, and that happened to be actually a carbon fiber. And if I open quickly that final outcome of that selection graphs that we had, so you saw we decided that based on those constraints, the best material is going to be an epoxy high strength carbon fiber reinforced composite made from UD layup. And I expressed some reservations on this as well because of the specific manufacturing method that will be needed, as well as the overall cost, because in this case the cost turned out to be around 7.12 which is for per cable, and this was the of the based on the material cost, not including other aspects of the cost. So this was what we did in the previous part of the case study. But then we said we have to see whether we can improve on this by making some of the variables as free variables. And this is something that we normally do at embodiment level in the design. So now, today, what we are going to be discussing is primarily linked to the embodiment level of the design, and where we are going to treat area as the free variable. And then we'll carry out the material selection, and then we'll decide the best option in this case. And we will also compare it with the option that we had in the previous case. Now, just like the previous case, we'll start with the translation, and in the translation phase, again, the function obviously has not changed, so it's still the same function that you are basically designing an axial tie, an axially loaded member in tension. And like I said, the main difference is that you're free to choose the diameter of the rope, and you are doing it to optimize your solution in terms of making it cheapest while meeting the other constraints that we have already imposed. And these other constraints I have reiterated here for you. So the length is 3 meters, the maximum static force is 10,000 newtons, maximum deflection is 5 into 10 to the power minus 3 meters, which is 5 millimeters. Maximum mass should be less than 1 kilogram. And although we are not treating this as objective, we are just kind of putting the upper limit on the mass. Obviously, the lower it is, the better, but we're not directly treating it as an objective. Rather, we'll use this as a constraint later on. But I'll show you that you don't really need to directly input this from the start to make sure that you are making use of this fact that the diameter is actually set as a free variable. We chose a very large factor of safety of greater than 6, and this was because we expect this cable to be used in a dynamic scenario where one of the cars will be stationary and the other car will ramp up the velocity. And as in the other part of the course, I discussed the method to determine the effective force in case of the dynamic loading, and it turns out to be that for this type of a rope with the typical kind of constraints that I've used over here in terms of the length and the deflection, you end up with a force which is typically between 5 to 7 times larger than the static force. So that's why I've chosen 6 as a safe estimate here for the factor of safety. In terms of our assumptions have not changed. Our assumptions are still the same. We are accounting for the impact loading using the high factor of safety. We are ignoring the effect of twisting of the strands. So we are just considering this cable to be one solid circular cross section. The free variable in this case now has changed. So this is now the choice of area as the free variable, and therefore the diameter is also, we are free to choose that diameter or the radius of the cable. Choice of a material is of course the free variable, because that will then allow us to do the material selection. Objective here is to minimize the cost, and basically we'll be doing it to get the material with the lowest cost per unit volume. Next, after this, basically what we need to do as part of translation is to derive the material indices for material selection. So in this case, because the area is free variables, we are not going to directly start deriving the constraints. Rather, we will derive the material indices in terms of the variables of interest, which basically link these constraints with the material properties. So for example, the modulus of velocity will be linked with deflection, the elastic limit stress, the yield strength will be linked with the force and the area, and the density will be linked with the with the basically the maximum mass that is acceptable. Of course, all of this then now has to be done in relationship to the area being a free variable. So let's now look into that. So to do this, what we need to do is we have to look into the appropriate performance function. And again, this derivation itself is not necessary, because this is a commonly known function. So you can actually go on to the CS like I showed you in the last video and just simply plot the index directly from there. But it's always good to put some of this information on the paper first, so that you can identify correctly the different relationships of those performance variables, especially when you are dealing with multiple constraints. So that's why I'll go through it step by step. So in this case, what we have is, if Cm is the cost per unit mass, then we can express our cost or per unit volume as cost per unit mass times the mass itself. So this mass can be written in terms of the geometric variables of area and length, and the material property of density. So it is AL into rho, which is area, length, and density. For if we are looking at the things from the point of view of the stiffness constraint or the Young modulus constraint, we have the basic 1D relationship where we can say that your delta is equal to FL over AE, or therefore the area will be force times the length over delta, which is the allowable deflection in this case, and the Young's modulus. And when we substitute this area back into this equation, we get basically the first estimate of our cost, which is then FL square over delta into Cm, which is per cost per unit per kilogram, into density divided by the Young's modulus. And in this case, of course, the force, length, and the delta is a fixed constraint, so this will be a constant, whereas this represents the variables that we can change to change our material selection, and therefore we'll call this as our material index M1. For the strength constraint, if we consider the strength constraint, we can again have a definition of area based on the relationship of force with the yield strength. And if you notice here I have actually used the force multiplied by the factor of safety to account for the fact that it is going to be used in a dynamic scenario, and we have the factor of safety based on that we have the factor of safety to account for that increased value of the force, and to keep the rope safe, we will have to make sure that the yield strength is actually less than the actual stress in the bar. Based on that relationship, we have the constraint on area as F over FOS, F into FOS over the yield strength. And when we substitute this back into this equation over here, so we are able to get the second estimate of the cost, which is F into FOS into then length into Cm, which is again the cost per unit mass, into density over sigma yield. Now, with this understanding, we have got our two performance indices. The first one is this one, which is based on the cost per kg into density over elastic modulus, and the second performance index is cost per kg into density over yield strength. So now what we can do is, I mean, we can actually start going and plotting these material indices. But again, like I said, I want to first of all see all the relationships. So I want to see how, if we are, if, because now we have to deal with both of these constraints and we have a separate value of area. So in reality, what will happen is that one of the constraints can actually dominate the design. So maybe the area that you get from the strength constraint will be the requirement of area will be larger, let's say based on the strength constraint, then you'll go by that estimate. And if the requirement of area by the deflection constraint is larger, then you go by that, because obviously both of the constraints have to be satisfied. So that's why we need to look into both of these simultaneously. So that then takes us to the concept of coupling constant, which again, we discussed in detail in our lecture sections. And there in the lecture session, I discussed this with you, and I said, well, we have to decide as a designer that which of these constraints is more important for you as a designer. And I just to for those who may have forgotten the point where we discussed this in lecture, so let me bring up that slide as well. So this was where we were discussing this point, and we said that now we have to decide that which constraint we value more, and we choose the material that basically is offers us the minimum possible option. So in this particular case, we will follow a similar procedure, and we will basically start by first thinking that, okay, let's give equal importance to both material indices and then see if we can improve our material selection or not. Now, in this particular case, we are saying that we are giving equal importance to both material indices simply because we don't have any other basis to say otherwise. We have already increased the force in the dynamic case by the factor of safety for the strength calculation. So in some ways, you can also think of that we are actually valuing the strength more in this particular case, because really the deflection, once we know the static deflection, we are trying to just work with that to kind of keep our impact force in a certain limit, and we don't want to unnecessarily put extensive constraint on the deflection itself. So, with that assumption of equal importance, we therefore have we can derive the we can equate both of the costs, and we can say, okay, in this case, the cost one is equal to cost two, and that's the scenario. So we replace it with the performance equation. So we have F into FOS into L, which is the basically because of the strength constraint, the cost because of strength constraint, and this is the cost because of the Young's modulus constraint. We rearrange both the variables, and basically what we then get is the Cm over rho into sigma yield, which is our M2, right? So this was our M2, is equal to this L over FOS into delta into M1, which is our material index 1. So that basically this term L over FOS into delta actually defines our coupling constant. So this will allow us to place our line at the correct location on CES. Now putting the values of the given constraint with the L length being 3, the factor of safety being 6, and delta being 0.05 or 5 mm, we get a value of coupling constant to be 100. Now keep this in mind, this factor of safety choice is again a design choice, and that will depend on the scenario. In this case, I've suggested the value of 6 based on my previous calculations for the impact force. But in other situations, you may want to actually carry out a what-if analysis. So for example, if we just have the factor of safety as 1 and we are not really dealing with a dynamic equation, then the CC or the coupling constant will change to 600, and it will give you a very different set of choices for the same problem. So it is important to carefully consider the factors that are involved in determining the coupling constant. Then after this, we will start calculating constraints for material selection. So basically for the screening purpose. And in this case, we can apply the constraint for the given mass in terms of the strength, and we can also apply the constraint for the given mass in terms of the stiffness. So we'll deal with them separately. Again, this is not a necessary step in this approach when we're treating with area as a free variable, because a lot of time we are doing this with trying to carry out what if analysis, but I would prefer putting some of these constraints to make sure that we have the unreasonable choices ruled out at an early stage. So the mass, which is being limited to 1 kilogram in this case, again is given by the same equation, that is the volume into the density, which is area into length into density. Now, using the force area relationship that we just discussed earlier, we can write down the mass as F into FOS into L into sigma over sigma, into rho over sigma yield, which is density over sigma yield. Rearranging this basically allows us to write our constraint on density over sigma yield in terms of mass and F and FOS and length. Now, putting the values from the given condition of m less than equal to 1 means that the value of density over sigma yield should be limited to 5.56 into 10 to the power minus 6. So all I've done is I put the value of 1 in here for mass, I put the value of 10,000 newtons for the force, I put the value of 6 for the factor of safety, and I put the value of 3 for the length, and I come up with this constant. Now I can then later on use this in the CES to apply the constraint as well. Now from this, I can actually also, like I said, calculate the constraint for screening in the scenario 2 in terms of the stiffness. So in this case, the main difference is that now the area, which is the free variable, will be substituted using the area force relationship. And when we do that, basically we can get a new value for mass in terms of the substituted area as FL over delta E. So we actually end up with FL squared over delta into density over Young modulus. Again, separating the material index on one side and keep moving all the constants on the other side, we can then work out the constraint on the value of density over Young's modulus for the case when mass should be limited to less than 1 kilogram. And therefore, we say that any material which has the value of density over Young modulus less than 555.6 into 10 to the power minus 9. So again, this value has been calculated by putting this as 1, putting this value as 5 mm, and putting this as 10,000 newtons. Sorry, 1,000. 10,000 was the applied force, and then keeping this length as 3. So this gives us the other constant that we need to apply as a constraint. Right. Now, once we have all the constraints and the coupling constant and everything, we will actually now go on to the CES and apply these constraints and create our charts. I have given a step-by-step approach of how you should do that, right? So I've divided this into 6 steps, and I'll follow this now in front of you. So okay, so we'll now run the Granta software, and we'll carry out this analysis using a level 3 database. Actually, I'll use level 3 aerospace database. Um, and I will be now looking at all of my material options. And to do this, I will now start using the chart index tool, and I'll keep this on the other side, the set of slides, because I'll need to look into the functions that I need to plot. So the first chart that I'm going to plot over here is going to be based on my material index, which I discussed with you, is basically with y-axis being Cm rho over sigma yield and m1 and x-axis being Cm rho over E. Now, as I explained, it is sometimes easier just to use the built-in performance index finder. So that's what I will do in this case. So I'll go into tie intention, and I know that my y-axis has a constraint on the strength, and I'm optimizing it for cost. And you can see here the form of the equation is exactly same as what we derived earlier. So this is basically our correct material index. On the x-axis, I will be basically plotting the again using the performance index finder. I will be plotting the the material index for with the limits on the stiffness and with the optimization with regards to cost. And again, you can see section area is 3, so you've got the correct material index over here. So with that selected, you have now all of these materials that are being shown to you in this graph right now are the correct set of materials for this particular case. Okay. So this is on this axis you've got the cost per unit of strength, and on this axis you've got the cost per unit of stiffness, and you've got your function written as well. Now, once you have this graph, like I said to you, you can actually start directly now plotting the line, and you can actually plot the line of the relationship between these two constraints. So this is my M1 and this is the other one is my M2. What I'll do is I will actually write down here M1 and M2, so it's actually clear to you that which of these functions is M1 and which of these functions is M2. So I'm just worried maybe it will just eliminate the subheading there. No, it doesn't. That's excellent. So similarly, I will write here M2 just to clarify and have a consistent description based on what we discussed in the slides. Now I can write down the equation between these two, and I just need to go on to my index line. Right now I'll just do it for display purpose. Okay, so like I said, I've just arbitrarily placed this line anywhere, but then based on what we discussed in the slides, we now have to input the value of the coupling constant. So now what you need to do is to make sure that the line is passing through the correct point on the chart. You have to put here x as 1, and then the y value will basically be the value of your coupling constant, which is 100 in this case. Keep this in mind that you are plotting this on a log-log chart, so these numbers need to be actually applied exactly in the same manner. So for the coupling constant equation, always keep your x as 1, and then y should be the value of the actual variable cc that you have determined. So for example, in our case, we determined the value of cc to be 100 in this case. So that's what I'm using over here. So as soon as I click OK, it actually jumps to this point. So now what I know is that any material that is passing through this line is basically meeting the is basically showing us the compromise between the cost per unit stiffness and cost per unit of strength. If you choose the materials on this side of the line, they will be more optimized for cost per unit of strength, and otherwise if you choose it on this side. So basically this is what was meant by saying that it is either constraint 1 dominant design or constraint 2 dominant design. Now, right now, if we just select, like I was saying in the lecture, right, you can then choose the material which is the minimum over here, and we can actually then try to find out. This is not necessarily going to give us the correct options. The reason being that right now we have not put any limits on what will be acceptable materials for the given set of input data that we have. So we have not applied the constraints. So in this case, then we will basically move on and we will actually apply these two constraints, the one that I applied on density over yield strength based on the given values of mass and the force, vector safety, and length, and we will apply this constraint on the density over Young's modulus based on these input given conditions again. But you cannot apply these directly on this graph because this is for cost per unit of strength and cost per unit of stiffness. So for this, what we'll need to do is we have to then plot two more graphs. And I will therefore come back to this graph later on for the actual material selection. And on this graph, I can I can just simply input my function on which I want to use to apply the constraint. So in this case, my first constraint is shown over here, right? So this particular value, right? So density over sigma yield. So I can input that function over here as density or divided by yield strength. Now, you may not remember the name of the exact variable. So in that case, what you can do is you can actually go to the mechanical properties and then scroll down to the correct quantity. So in this case, it is yield strength. So you have to write it exactly in the way that CES describes. So it's better sometimes to just simply pull up the value from the actual drop down rather than to type it. So that's going to be my quantity on my y-axis, and I'll say OK. And then on my x-axis, I'm plotting my other constraint quantity, which is basically density over Young's modulus, right? So again, this is now density from the set of physical properties. So it is density divided by Young's modulus in this case. So that's here. Right. Now with these defined, again, we are just sticking with the default of the logarithmic graph, and I'll just say OK, and this then plots a second graph for us, a second stage for us. On this graph, if you want to limit the value of this function, density over yield strength, all you need is actually a horizontal line. So I'll say the slope should be 0. Now because this is your kind of your upper limit, because we are saying here that the density over sigma yield should be less than this number, so I'll use it as a minimizing index. So I'll just say minimize. And then I'll click anywhere on the graph because I need to then adjust the value. So to adjust the value, I'll right click and I'll click on properties. And in this case, I don't care about the x value, whatever it is, because it's a horizontal line. I just need to input the value of the y, which is basically representing this condition. So it is 5.56 into 10 to the power minus 6. So I will enter it exactly like that. So 5.56 e minus 6. So that's the maximum acceptable value. And you see my line has moved over here, and you can see that a whole lot of materials have actually been simply filtered out because of this. Okay. Next, what I will be doing is I will be applying the constraint on the density over Young's modulus value. So I'll be just simply going on to the index and display line. And this time I need a vertical line to apply this constraint. So I'll just say OK, and I'll then put it anywhere here. And again, now I will go click on properties, and I need to remember that this is also in the minimization format, right? So because it is in minimization format, so I will accept any values which are greater than, which are less than 55.6 into 10 to the power minus 9. And this time, this has to be entered in the x-axis because you see, it's the vertical line, so we don't care about where it is, what is the point on the along the y-axis, but we care about the location along the x-axis. So it is 55.6 into 10 to the power minus 9, and I'll say OK. And now you see that we have got this set of materials which is remaining, and our results over here are saying that we have got 357 materials available. Now, to make things more easy for us to say to select, what I will do is I will actually eliminate the materials which are not in the bulk form. This is to make sure that the choices that we are getting are reasonable from the point of view of making a cable. So once I do that, I get rid of some of those fibrous materials that are there. So I can actually show you some of those options that were there earlier, these black options. So these are some of those fibers. So because I'm not saying that going to use for this cable the materials in their pure fiber form, I'm going as bulk material choices. That it obviously it will not eliminate other choices like the composites and other options that we have, and actually we can see for example the epoxy carbon material that we selected is actually somewhere over here, but this was the selection in scenario one. Right now this is not the selection. Okay, so keep that in mind. I just picked it up to highlight one of the options. Now we can go back in our previous graph, and this now seems to be much less cluttered, as you can see. And now if you look into this line, which is the line of our coupling constraint, you can again check that it is passing through 100 over here. So you can see here that clearly on this line the minimum option that you have is actually this one, which is cast iron austemper ductile steel. And then the second best option over here is this one. Sorry, I think I just moved the line slightly, so I'll just adjust it again to pass through 1 and 100. And now if I can click on this material option, so it is a low alloy steel, AISI 9255, oil quenched and tempered. So these are my two best candidates according to the conditions that I have set. There are other steels as well, but they have been eliminated because of the constraints that we have. And you can actually think about it as well from this point of view. If we had not applied those other constraints, we could have moved this up and down and then seen some effect on some of those choices, because you see not everything has to be completely fixed at embodiment level, and you can carry out multiple analysis like this. But in each analysis, you have to obviously list some of the things as fixed and some of them free. In this case, we are obviously considering our area to be free variable with the rest of the constraints kept same as the last case. So you can see here that our best choice has shifted significantly. But let's now put some numbers in to make sure that the selection that we are getting is actually valid selection. So you can open the data for this one and actually input this data. You can either do this manually or like I have done over here. I've done a bit of comparison using Excel. So I've got the data from my scenario one calculations. So these were all my scenario one calculations done earlier. And now we have got the scenario two calculations, and I've put the data for these two top candidates over here from directly by noting it down from CES. And I've actually done it for the whole range. So I've put the minimum and the maximum values from CES and compared them. And what I want to highlight over here in terms of this comparison now is that, our best choice, which was this one, cast iron austempered AIDI 1600, which is a ductile steel, right? When we do this, we are able to see that we actually meet our mask constraint for both the bottom values in the range as well as the top values in the range. But the cost is the most striking thing is the cost, because the cost here is only $0.4 for the cable, whereas when we were keeping the area as fixed variable and we had arbitrarily chosen a 5 diameter, we were only able to get the minimum cost as $7.12. So this is a substantial reduction, almost 14 times or more than that, definitely more than that. And if you think about it in context of, let's say, a million of these have to be made, here you will be spending around 7 million for a million of these cables, whereas in this case you will be spending even less than a million. So it's half a million or even less actually. So that's the sort of comparison that you can have by correct choice of material at at the at embodiment level, because you're not unnecessarily fixing the variables, and you can do this even with the comparison with the second choice is actually also interesting, because even with the second choice, yes, we are achieving the mass requirements, but the cost is still higher. It is $0.9 per cable, whereas here it is $0.4 per cable. So again, this is more than double the cost here, and here you can clearly see that the cost is more than 5 times. Interestingly, although we normally consider the carbon fiber and other composites to be much lighter, which of course they are based on their density, but in terms of the actual mass of the cable, you can actually evaluate that for this particular cable. If I want to evaluate the mass, then it is basically, let me just put down the actual volume first over here, and then I can reevaluate the mass. So, and multiply this with the actual density of my epoxy composite from the list, and I can go back to this chart because I already pointed that out. So my epoxy composite's density is around 1.55 to 1.58. So let's say even if I take the average value of 1.56, I call it as 1.56 into 10 to the power 3, you can see here that the mass is 0.37 kilograms, which is not too far away from the mass that I'm getting with this 14 times cheaper cable. It's insignificantly different from that. So you can see here that how our material selection has not only allowed us to get the best material in terms of cost, but also satisfying the remaining constraints. So we can, of course, use this procedure to carry out further what if analysis as well. And I did some cases where, for example, I moved this line over here, but then I have to, of course, relax these constraints as well correspondingly. And that would be the case then, where you do not have a very high factor of safety, then you will be here somewhere in with this coupling constant line. So I encourage you to go back and actually try these what if scenarios as well and go through this whole case study. And I hope you are now convinced that you know how much cost a simple, correctly set up material selection case study for your actual design can actually give you. So thank you very much for that. And if you have any questions, you can, of course, ask me or any of the other instructors in the lab. And so with this, I will close this recording now. And thank you.